Hello, my name is Shin here. This technology I'll explain here is one I discovered during my long tenure at a top Japanese company, when I realized the true nature of quality that had not improved despite the company investing a lot of resources into it, and I described a way to improve it. I used this technique to ensure product quality in some of the most cutting-edge automotive technologies of the time. For a long time, this technique was not understood not only by my company, but also within Japan. Therefore, I would like to make it widely understood in English-speaking countries. This technology was previously published in a book titled Baratuki no Taisyogo How to Deal with Variance by Jujutsu Hyarancha in Japan, and was presented as a paper at the Japan Society of Mechanical Engineers Computational Mechanics Conference and Reliability Engineering Association of Japan Reliability Symposium last year. Here I'll introduce the contents of the latter presentation. First, I'll explain the problems with the standard deviation and Monte Carlo methods that are currently used. Then, I'll explain how to address these problems. Finally, I'll compare the accuracy of the application examples of dimensional design and ship wake simulation. For us engineers, the problem with existing technologies for ensuring quality in various products and services is that there is error in the target values of parameters with variance, and these values are ambiguous. The standard deviation guarantees probability on the assumption that the variance follows a normal distribution, but in reality, the distribution has various shapes depending on the manufacturing method and the environment in which it is used, resulting in errors. I will explain later that the Monte Carlo method does not guarantee the distribution of results. In other words, the inability to reflect the distribution shape of actual variance in the calculation results generates errors, and I think that not seeing this often leads to malfunctions, excessive quality, and compromised performance. First, let us consider the prerequisite under which the Monte Carlo method can guarantee results distribution with the time series calculations written here. The colored dots are images of data, and let us assume that the law of large numbers holds and stability is achieved with m pieces of data. A distribution that is stable with m pieces of data means that if random numbers that follow a distribution are generated and a histogram is created by dividing the parameters into n pieces, the shape will be almost the same as the original distribution with m pieces of data, and it will remain stable even if the number of pieces is increased beyond m pieces. If v is a speed distribution and x is a position distribution, and both are independent of each other and stable with m pieces of data, how many repeated calculations will be required for the distribution x plus v after 1 second to stabilize? Let us consider the prerequisite for stability in xy in space. If x and v are mutually related and the correlation coefficient is 1 or -1, then when v is determined, the corresponding x is uniquely determined, so there is no freedom of change and it will stabilize with m pieces. However, if the correlation coefficient is 0 and they are mutually independent, the combination's area of x and v are spread throughout the entire green frame, and even if a parameter of v is determined, there are n possible partners for the corresponding x. In other words, when a combination of multiple independent events has an effect, even if the law of large numbers applies to each individual event, there is still combinatorial freedom remaining for the whole, and the law of large numbers does not apply when there are m events. I believe that at least m² calculations are required to reflect all the information. Furthermore, if there is variance in acceleration and the velocity distribution of v changes significantly every second, let's consider the prerequisite under which a correct distribution will be obtained after 10 seconds. Based on the previous idea, we believe that m² calculations are necessary to ensure that the position after 1 second has a correct distribution. After 2 seconds, m³ calculations are necessary. Furthermore, to guarantee the distribution of the position after 10 seconds, m to the 11th power calculations would be necessary, and these types of calculations are unrealistic. I believe that the reason for this is that the parameter combination that guarantees the probability is chosen at random hit and miss. Therefore, in order to correctly reflect the distribution shape in the calculation results, it is more reasonable to divide the distribution parameter method and take into account the combination to guarantee it. For example, if distributions a and b are divided into 3, the corresponding division of a plus b will be 5. There are 3 combinations where the parameter of a plus b is 2. A and b are 0 and 2. 1 and 1. 2 and 0. The sum of the products of the probability values of each combination is the probability of 2. The distribution of a plus b is obtained by calculating this with 5 parameters. By defining a minute division method for each calculation in this way, it is possible to guarantee the distribution after various calculations with m pieces of data. This is distribution calculation and distribution integral. This means that by expanding the calculation object from a numerical value to a distribution, the probability is guaranteed from a point to a region. First, regarding the four arithmetic operations, I'll explain the division and combination in xy space when calculating distribution z after calculation from distribution x and distribution y. In the case of addition, the combination of x and y that results in point z1 on z is on this red line. If you divide this line and add up the products of the probability values of x and y as before, you can find the probability value of z1, and do the same thing for all z to find distribution z. In multiplication, the combination is found on this hyperbola. In division, the combination is found on a straight line passing through the origin. This is the distribution operation. I wrote an explanation of the multidimensionalization of this operation and examples of its application to the design of various hardware and software in my book, Baratsuki no Taijouwo. It means how to deal with variance published, so please refer to it if you are interested. Next comes the integral calculation, where the position distribution x is calculated by successive integration as shown in this formula. The xv space, which is composed of position x and velocity v, is divided into infinitesimal parts, and each grid is assigned a position, velocity, and probability value, and updated in a time series. When the grid position after dt seconds is calculated from each position and velocity, a diamond-shaped area like this is obtained. After a further dt seconds, this area is obtained, and it changes like this after n seconds. By dividing the position range after n seconds into equal intervals and adding up the grid probability values for each division, the probability value of the position distribution can be obtained. This is the distribution integral. Using the above technology, we have now released a programming environment on GitHub that can handle complex simulations. Next, we compare the accuracy with existing methods. First, I select the correct distribution and generate random numbers that follow that distribution. Using these random numbers, I generate a kernel distribution using the same data as the results of probability calculations using standard deviation and the Monte Carlo method, and compare the results of the distribution calculation. I generate 6 sets of 4 patterns of 100, 500, 2000, and 10,000 random numbers, and examine the fluctuation and error in the resulting probability values. A distribution calculation is performed using the initial correct distribution, and the difference between the two calculation results is considered to be the error. As a first application example, I compared the defect rate due to component variance in dimensional design with the conventional method. Calculate the probability that components A to C cannot be assembled because there is not enough space when assembling them within the frame of component X. When using standard deviation as the conventional method, if the dimensions are separated into nominal dimensions and variance, and the portion where the variance is plus or minus the nominal dimensions follows a normal distribution, it is possible to calculate the probability of defective products occurring when the allowance dimension is a certain number of times the standard deviation sigma. For example, if the allowance dimension is 3 sigma of the variance, the defect rate will be 0.15%. In this case, the overall standard deviation sigma is the square root of the sum of the squares of the sigma of each part. I think the conventional method is to determine the defect rate by integrating the allowance of the nominal dimensions as a certain number of times this overall sigma. As mentioned above, the standard deviation guarantees the probability value on the assumption that all variations follow a normal distribution. However, actually produced products have distributions of various shapes, and the probability value guaranteed by the standard deviation sigma will change significantly if the distribution shape changes. It is common for distributions to become biased like this due to production circumstances, and I think it is normal for the target value to be shifted to match the distribution bias to the design dimensions, or for it to extend to the very limit of the allowable dimensions. In designs using distribution calculations, instead of separating nominal and variance as in the past, dimensions are treated as distributions. Parameters with variance are treated as histogram-based distributions based on data. Not only the feasibility of dimensions such as whether a component fits within a frame, but also the feasibility of general designs such as systems, software, and hardware, can be designed probabilistically by comparing the distribution after calculation with the target distribution. In this case, the probability distribution of the sum of the ABC distributions and the cumulative distribution of X are lined up along with their parameters, and the distribution of the product of the probability values for each parameter is found, and the resulting area is the probability that the left distribution exceeds the right distribution. To find the probability that the left distribution exceeds the right distribution, the overlap distribution is found as the cumulative distribution of the right distribution. This makes it possible, for the first time, to evaluate feasibility that accurately reflects variation. In other words, by reflecting the actual distribution shape of each part, accurate probability values can be found, ensuring quality. Based on the above ideas, we compared the defect rates when parts X and ABC are mass-produced. Let's assume that the dimensions of the parts follow the distribution shown below. This figure shows an example of creating a kernel distribution by generating 110,000 random numbers that follow the distribution of part X. 6 sets of random numbers were generated with 4 patterns: 100, 500, 2000, and 10,000. Similarly, kernel distributions are generated from random numbers for parts A, B, and C, and a distribution is created by adding up the 3 distributions. To find the probability that the total of the 3 exceeds dimension X, we arrange the probability distribution of the addition result and the cumulative distribution of X, which looks like this. The defect rate is 2.21%. We compared this with the defect rate calculated from the standard deviation using the same random numbers. This is a comparison of the accuracy of standard deviation and distribution calculations, with the horizontal axis representing the number of pieces of data, 100, 500, 2000, and 10,000. The vertical axis shows the minimum, maximum, and average value of the probability value error calculated 6 times. When the number of pieces of data is small, there is a fluctuation of about 2 to 3%, but as the amount of data increases, it converges to a specific probability value. However, the probability value of the standard deviation converges to a value that is off by about 1.5%, and we believe that this is an error caused by the distribution shape. Next case, as an example of simulation design. I estimate the amount of variance in the arrival point due to randomly changing wind direction and speed as the trajectory of a ship traveling in a certain direction changes. I assume that wind direction and speed change randomly according to the following distribution. This is a simulation of the ship's wake using Monte Carlo simulation, and we find the probability that the arrival point will fall within this red frame. Between 110,000 random numbers that follow the probability distribution of wind direction and speed are generated in the same pattern as the dimensional design. This heat map is a 2D histogram of that. These random numbers are selected randomly on a regular basis and the wake changes. This is the wake overlaid in a Monte Carlo simulation. In a Monte Carlo simulation, the arrival point after a specified time appears as a scatter plot like this, and the number of times it arrives within the yellow frame is counted to find the probability. In the case of distribution integrals, a kernel distribution is generated from the same random numbers. These red contour lines are the kernel distribution. As with the Monte Carlo method, a distribution simulation is performed assuming that wind direction and speed change periodically, the distribution of arrival points is found, and the volume of the distribution that falls within the same frame becomes the probability. This is a comparison of the accuracy of the Monte Carlo method in distribution integral. When there are around 100 to 2,000 random numbers, there is no doubt about the amount of fluctuation in both. When there are 10,000 random numbers, the fluctuation in the distribution integral is only 1/3, so it appears to be more accurate, depending on the type of simulation. The Monte Carlo method may be difficult to converge in some cases, or easy to converge in other cases. For simulations where the calculation results tend to be dispersed, fluctuations remain even with a large amount of data, so the distribution integral is thought to have the advantage in terms of accuracy. In conclusion, distribution calculations and distribution integrals make it possible to calculate the probability of various models, and accurate probabilities can be obtained if the distribution shape of the source of calculation is correct. However, when converting data to a distribution, there will be errors when converting to a kernel distribution if there is little data. Methods that assume normal distribution, such as standard deviation, have errors due to differences in shape from the actual distribution, and the more the distribution is biased and there are independent variation factors, the larger the error becomes. This can be improved by distribution calculations. The Monte Carlo method can simulate realistic distribution shapes by inputting them, but even if the amount of data and the number of calculations are increased, error fluctuations remain, so in some cases the distribution integral may be more accurate. In the future, I'd like to extend the distribution integral to various simulations and compare it with existing methods. In the above, I have stated that treating variance as a distribution and treating the distribution as a calculation subject in the same way as numerical values leads to a fundamental understanding of variance and improved accuracy. In the book I introduced first, I have described how variance affects quality, details of distribution calculations, judgment indicators using distributions, specific methods for designing hardware, software, and systems, the essence and prerequisites of engineer morality, and more. If there are any publishers willing to publish an English version of this book, I would appreciate an introduction. Thank you.